you've got this graph over here. We're going to get you all to the point where you don't need the graph. I just want to be able to give you the function and that all the information you need is over here. But there's a point I want to make with this graph. We're looking at the function 10x minus 2x squared over x squared minus 4x minus 5. Let's have the horizontal asymptote conversation. Horizontal asymptote, take the limit as x approaches infinity, 10 times x minus 2x squared over x squared minus 4x minus 5. Well, what happens there? In the numerator, I have 10x minus 2x squared. That graph it's quadratic. The leading coefficient is negative, so it is an upside down parabola. We're doing something like that. If it's an upside down parabola, then as x approaches positive infinity, the y value approaches negative infinity. In the denominator, x squared minus 4x minus 5, that is a parabola that opens that way. As x approaches infinity, the y value approaches infinity. These do not cancel. This is our second indeterminate form. We need a new algebra trick. And this was the algebra trick that I shared with everybody. And let's see what happens. We're going to take 10x minus 2x squared over x squared minus 4x minus 5. And we're going to multiply this whole expression by 1 over x squared in the numerator and 1 over x squared in the denominator. What is that? That is our old friend, Fancy 1 from middle school. And you may not know where this is coming from. Some students have figured it out. The way you determine what version of Fancy 1 to use, you look for the highest power of x. In this case, it's x squared. We're going to multiply the numerator and the denominator by the reciprocal. Let's see why that is helpful. We take the limit as x approaches infinity, distribute 1 over x squared through to both terms. You'll have 10x over x squared, which reduces to 10 over x, minus, you'll have 2x squared over x squared, which is 2. In the denominator, x squared times 1 over x squared is 1. 4x times 1 over x squared is 4 over x, minus 5 times 1 over x squared, 5 over x squared. That might look worse, and I would agree with you. That looks worse, but let's see what happens. What happens as x approaches infinity? 10 divided by something heading off to infinity gets closer to 0, and negative 2 stays as it is. In the numerator, 0 over negative 2. 1 minus 4 divided by something over infinity gets closer to 0. 5 over x squared gets closer to 0. We have 1 minus 0 minus 0, negative 2 over 1. We have then shown that the limit as x approaches infinity of this expression is equal to negative 2. What did we really just show? We have a horizontal asymptote at y equals negative 2. If I look at the graph, this is the line y equals negative 2. I can see that as x approaches infinity, this graph is decreasing towards that line. I could do the same process and see what happens as x approaches negative infinity, and we would see that the y values will get closer to negative 2. Great. Let's talk about the vertical asymptote. What a lot of students learn in Algebra 2 and in pre-calculus is in order to find the vertical asymptote, you set the denominator equal to 0, x squared minus 4x minus 5 is equal to 0. We factor it. Use your mama diamond if you'd like to. I do some old school factoring to get x minus 5 times x plus 1 equals 0. How does that work? X minus 5 equals 0, or x plus 1 is equal to 0, x equals 5, or x equals negative 1. It appears from the work that we've just done that we have two vertical asymptotes at x equals 5 and x equals negative 1. When I look at my graph, though, Over here at x equals 5, I don't see that the graph is getting closer to infinity or negative infinity. I just see the graph gets closer and closer and closer to some point over here. It happens from the left and from the right. At x equals -1, we have the behavior that we expected. The graph increases towards infinity. It decreases towards negative infinity. This fits a vertical asymptote at x equals -1. But what's happening at x equals 5? What's happening has to do with the fact that you have what we call a removable discontinuity. Let's go back to the original function. H of x is 10x minus 2x squared over x squared minus 4x minus 5. Let's look at this like an algebra student. The numerator, I can factor out 2x to get 5 minus x. The denominator, we factored once before as x minus 5 times x plus 1. The 5 minus x and x minus 5 are opposites. Opposites cancel out and leave you a -1. And we get -2x over x plus 1. This is a equivalent form of the original problem. It is different in that we eliminated these factors of x minus 5 and 5 minus x. What happened is we removed the problem in the denominator. But we know x equals 5 is an excluded value from the original problem. We don't want the denominator to be equal to 0. In the simplified version, it's gone. When that happens, we call x equals 5 a removable discontinuity. Otherwise known as a hole. You have a hole in the graph at x equals 5. Because of the resolution of the program I was using, you can't actually tell that there is a hole here in the graph. There is. I would encourage you guys at home, using your graphing calculator, graph this original function, not the reduced one. Graph the original, evaluate the function at 5, and what you're going to see is that your function is undefined. You have a hole. Okay. We're going to do one more with horizontal and vertical asymptotes. The function I'm looking at here says h equals 6 divided by 3 plus e to the x. Again, the graph has been provided on the right. Don't expect that on the exam. Expect that you would just be asked questions about the original function, but I wanted to have the graph available so that we could see what's going on. I want to find horizontal asymptotes, so I find the limit as x approaches infinity. 6 over 3 plus e to the x. We know as x approaches infinity, e to the x approaches infinity. 3 plus e to the x is going to then approach infinity, and 6 divided by something heading off to infinity gets closer to 0. So the limit as x approaches infinity of this expression is 0. That is confirmed by the graph. X approaches infinity. There we are. Get closer to y equals 0. Horizontal asymptote. Let's take the limit as x approaches negative infinity of 6 over 3 plus e to the x. As x approaches negative infinity, the graph of e to the x, we already looked at this before. Graph looks like that. As x approaches negative infinity, e to the x approaches 0. 3 plus e to the x approaches 3. And 6 over 3 plus e to the x approaches 2. So the limit as x approaches negative infinity is equal to positive 2. There it is. I see it in the graph. We have a horizontal asymptote at y equals 0. We have a horizontal asymptote at y equals 2. We can do all this work using our knowledge of calculus without the graph. That is going to be the expectation on the exam. Now let's look for vertical asymptotes. Vertical asymptotes. We set the denominator equal to 0. 3 plus e to the x equals 0. If I try to solve that, I get e to the x equals -3. We're going to take the natural log on both sides. Natural log of e to the x equals natural log of -3. Natural log of e to the x, we get x equals the natural log of -3. What this would tell me is I expect that when x equals the natural log of -3, I have a vertical asymptote. Well, what is the natural log of -3? This is undefined. We cannot take the natural log of a negative number. Since you cannot take the natural log of a negative number, that means the denominator is never going to be equal to 0. That means you have no vertical asymptote. All of that is confirmed by the graph. Again, you need to be able to do this without using the graph or the graphing calculator. These are some great examples to look at. I want to wrap things up with our conversation about infinite limits and all that other good stuff. So what we have is a rational function of the form, and by rational function, I mean a polynomial in the numerator and a polynomial in the denominator. When I have a polynomial over a polynomial, many of you guys have figured it out. What we do is we look at the highest degree. In the numerator, the highest degree is m. In the denominator, the highest degree is n. If m is bigger than n, if the numerator is larger than the denominator, then the limit as x approaches infinity is going to be infinite. That means that there is no horizontal asymptote. If m is less than n, if the numerator is smaller than the degree in the denominator, that means the denominator grows more quickly, we get 0 as an answer. So we have a horizontal asymptote at y equals 0. The last case, m is equal to n. The degree of the numerator and the degree of the denominator are equal to each other. In that case, we pay attention to the leading coefficients, the a sub 0 and the b sub 0. We have a horizontal asymptote at y equals a sub 0 over b sub 0. Those are just numbers. Those are the coefficients on your leading terms. Okay, let's apply that to these next three problems. I want the limit as x approaches infinity, 2x squared plus 3x to the 4th minus 31x over 8x to the 4th minus 31x to the 9th plus 12. The highest degree in the numerator is 4. Highest degree in the denominator is 9. Since 4 is less than 9, the numerator has a smaller degree than the denominator. The limit is going to be 0. Second problem. Limit as x approaches infinity, 2x to the 5th plus 3x to the 4th minus 31x. Now degree 5 in the numerator. 8x to the 4th minus 31x squared plus 12. 4 is the highest degree in the denominator. 5 is greater than 4. The numerator is of greater degree than the denominator, so the limit is going to be positive infinity. Last one, limit as x approaches infinity, 2x to the 5th plus 3x to the 4th minus 31x, degree 5. 8x to the 4th minus 31, oh, I meant for that not to be x to the 9th. I want that to be 31x to the 5th. So 8x to the 4th minus 31x to the 5th plus 12. Degree 5 in the denominator. Degree of the numerator, degree of the denominator are equal to each other. We're going to look at the leading coefficients. In the numerator, it's 2. In the denominator, it's negative 31. That's the limit, negative 2 over 31. That is it. My one cautionary tale to everyone out there, these tricks of you look at the degree in the numerator and the denominator will only work if it is a polynomial over a polynomial. You can use it for the limit as x approaches infinity and the limit as x approaches negative infinity, but only there. If it is anything else, don't use this trick.